Let's focus on buffers. So everybody has probably heard of buffers. What are buffers? Buffers are basically solutions that can resist a change in their pH whenever a small amount of strong acid or base is added. So any solution that if you can resist when you add acid into it or you add a small amount of base into it and it can resist a change in its pH, that is called a buffer. Okay. Now every buffer consists of two components. You cannot have a buffer without these two components. Okay. So it would either consist of a weak acid and its conjugate base, which is basically a salt of that acid. Okay, so it always has a weak acid and its salt, which is also called as its conjugate base, or it would consist of a weak base and its salt, which is also called the conjugate acid of that base. So it is always very important to remember that a buffer always has two components. It has two solutes in it. One of them is a weak acid or a weak base. It's never made out of strong acid or strong base. It is always weak. And then there is a salt containing that weak acid or a weak base. Okay, for example, this is acetate buffer, which consists of acetic acid and the salt of acetic acid. This is HF and the salt of this particular acid, which is NaF. Similarly, a basic buffer would consist of a weak base, for example, ammonia, it's a weak base, and its salt, meaning anything that has a salt made out of ammonia, which is example ammonium chloride, ammonium bromide, you could have anything. And similarly, this is N2H4. Anything that has nitrogen usually can act as a base. And if you make a salt out of it, like N2H5Cl, that's a salt of this, which makes it a basic buffer. One very important buffer that is our body has in its blood is essentially a buffer made up of carbonic acid. So it consists of an acid, weak acid, which is carbonic acid, H2CO3, and its conjugate acid or a salt, conjugate base or a salt, which is bicarbonate ion. So H2CO3 with HCO3 minus. How do they work? How exactly does a buffer work? So for example, you can see here on the top panel, what we have is an unbuffered solution, meaning it has no buffer in it. And in the bottom, we have a buffer solution. So if you take an unbuffered solution, the initial pH of both of these, buffer is 5 and unbuffer is also 5. So if you take these solutions and to each of them, you add 1 ml of strong acid. What happened to the unbuffered solution? pH went from 5 to 2. Whereas in case of a buffered solution, pH went from 5 to 4.98. So it resisted the change in pH. Similarly, if you take this solution in the first solution and you add 1 ml of a base, strong base into it, the pH jumped. If it is unbuffered, it jumped to 12. But if it is a buffered solution, the pH only increased by 0.02. It went from 5 to 5.02. So that is a buffer that it can resist change in pH. Whereas if you take an unbuffered solution, it will not be able to do that. So that makes sense why our body needs a buffer system, because we eat all this different types of food that are sometimes acidic in nature or sometimes basic in nature. Our body does a lot of chemical reactions which probably produce some acids or bases as byproduct, and all of that cannot affect the pH of the blood, because our cells or all the chemical reactions occurring in our body, they are very sensitive to pH change. So if there's a very slight pH change in our body, the cells will not be able to function properly. And that is why we need a buffer solution in our blood to be able to resist that change in pH. Now, how does this exactly work chemically when you think at molecular level? So a buffer, like we said, consists of HA, which is the acid, and its salt. This is the salt, which means this is the conjugate base. Remember, acid always dissociates to make a conjugate base. So I have an acid in my buffer and I have a base in my buffer as well. So this is the reaction that is usually occurring in a buffer. HA in water dissociates to give you conjugate base and ation. This is the equilibrium that is always established in a buffer. A buffer system is basically a chemical equilibrium between acid, weak acid and its salt, a weak base and its salt. So if this is my buffer solution, and let's say from outside you try and add a little bit of acid. If you add from outside a little bit of acid, remember equilibrium always tries to maintain itself by shifting the reaction in a direction where it can bring back the equilibrium. So the external stresses, you add acid. Now what will the acid do? Acid will react with the base because you have some base present in the solution already. It will react with the base and it will shift the equilibrium in the direction of the left, so that all the acid that you added from outside can be used up. Okay, so this is called as common ion effect. The buffer components are able to consume small amounts of base, which is OH ion, or acid by shifting in the equilibrium position. Okay, if you add acid from outside, the base will react with it. If you add base from outside, this acid that is present there is going to react with that particular base, and it will basically nullify all the effect of that base, and that's why the pH would not change much. It definitely changes slightly if you're adding a lot of strong acid or base, but it will still try to resist the change in pH as long as it can. Okay, and that how much change can it resist? That depends on the capacity of the buffer, how strong the buffer is. That strength of the buffer is called as buffer capacity. Okay, buffer capacity is the measure of the strength of the buffer, meaning its ability to maintain its pH following the addition of strong acid or base. So if you add a lot of acid or a lot of base, how long can it keep on resisting the change in pH? There is a point when you keep on adding a lot of acid or a lot of base, it will not be able to resist the change in pH. Okay, it will start changing the pH after that. But that range where the buffer can resist the change in pH, that is called the buffer capacity, and that depends on the strength of the buffer. And what does the strength depend on? The strength essentially depends on the concentration of the buffer components. Greater the concentration of the buffer components, the stronger or more strength is the buffer has to resist the change in pH. Similarly, it also depends on the closeness of the concentration of each of the components. So if you have the acid and you have the base or the salt out of it, as long as the two concentrations of each of these components are closer to each other, then the capacity is going to be greater. So the strength of a buffer, or how long can it keep on resisting the change in pH, it is called as the buffer capacity, which depends on its concentration of the components and how close are the concentration of each of the components. Now there's also something that is called as buffer range. What is the buffer range? The buffer range is the range of pH where you can use that particular component and create a buffer. Okay, so if you take a buffer and you try and make a buffer out of acetic acid and its salt, this is going to create a buffer which is going to be acidic in nature for you every single time. So if you try to use this buffer and you want to make a buffer at a pH of 8 or 9, something that can resist the change in pH at pH 8 or 9, then this is not the components that you want to use. Okay, because when you use these components, it would always give you an acidic buffer. So every weak acid or its salt, or a weak base and its salt, will have a particular range of pH where it can act as a buffer, and that range is called as the buffer range. Buffer range is the pH range over which a buffer is effective. So if you use it at that pH range, it will work as a buffer. If you don't, then it is not going to work as a buffer. Okay. Usually the answer to this, how can you know the buffer range, is simple. It is basically the buffer range is pKa, whatever is the pKa of your acid or pKb of your base, plus minus 1. The range where a buffer act as a buffer is going to be pKa plus minus 1. So if your CH3COOH, the pKa of this is, assuming, I don't remember the number, but assuming that's 4.7 pKa of acetic acid, then the range where this can act as a good buffer is going to be 4.74 plus minus 1, meaning minus 1 will give you 3.74 till 5.74. So this is the pH range where this is going to act as a buffer. Anything beyond that, you do not want to use a buffer made out of this. Look up different components and then use some other component to make your buffer. Okay. Now the next question is, how would you calculate pH of a buffer? Okay, so there are multiple ways you can do that. Remember, this is again an equilibrium system, which means if you want to calculate pH, you can draw ice tables. Ice tables are your answer for this question. Okay, but there is an easier way to find that pH as well. Okay, so we're not going to get into too much detail. For example, if this is my acid and acetate buffer, like I showed you before, what would be Ka of this? It would be product CH3CO minus multiplied by HI divided by CH3COH. Water is liquid, so we don't care about it because its concentration is not changing. Okay, so this is my Ka for the acid. If we take a general example, HA over water plus water gives you this. This is my Ka like I just showed you. Now if you put a negative log, if you take negative log of everything, what does it give you? Negative log Ka equals negative log of all of this. If you try and open this up, like separate all these components, it would give you negative log is equal to negative log of HIN plus negative log of A minus divided by HA. Remember, when you have multiplied two numbers and you take log of it, it becomes plus in log. What is negative log of Ka? Negative log of Ka is pKa. What is negative log of HIN? It's pH. Negative log of HIN is pH. So I can basically replace this with pKa, replace this with H, and what is this? This stays as it is, minus log of A minus and HA. Okay. So now because this is negative right here, this gives you Henderson-Hasselbalch equation. You can rearrange this equation to get rid of this negative sign. You rearrange it, pH is equal to pKa plus. If you move this, or because this is negative, to get rid of this negative, if I add log A minus over HA here and I add it on this side, log A minus over HA here, it would give me pH. To cancel this out, it would give me pH is pKa plus log of A minus over HA, and that's what this is. pH is pKa plus log A minus HA. This is the equation that would be answer to all your questions. So if you have this equation, you do not have to use ice table in case of buffers. This equation is called as Henderson-Hasselbalch equation. Okay, you don't have to understand how this was derived completely. I'm not going to ask you to derive this equation, but as long as you understand where is this equation coming from, you're okay. Okay, so you can see we did not make something new up. We just rearranged our equations to get to this equation. So this is called as Henderson-Hasselbalch equation. Remember this, pH is equal to pKa plus log conjugate base over acid for a weak acid, or it's also written like this, salt over acid, conjugate base A minus, right? If your acid is HA, its conjugate base is A minus. So A minus over HA, which is base over acid, or A minus over HA can also be written as salt over acid. So this is if it's an acid. If it's a base, your equation changes to POH equals pKb plus log acid over base, conjugate acid over base, which would be POH equals pKb plus log whatever is your conjugate acid over the base. Okay? So those are the two equations. Those will be given to you for every single exam. You don't have to memorize it, but you should know how to use it. Okay? This would make our life a lot easier. So for example, if you have to find pH of a buffer solution now, the question is calculate pH of a buffer solution consisting of 0.5 molar CH3COOH and 0.5 molar CH3COONA. Ka of acetic acid is given to you. So first thing you have to recognize, this is a buffer. Remember, now we have added one more type of solution or mixture that you have to find pH. So always if the question is calculate pH of something, you have to first identify what do I have in solution. Do I have a salt? Do I have a strong acid or a base, weak acid or a base, or now something else is added, which is a buffer. So if you have a buffer in solution, the answer is pretty simple. Answer is pH is equal to pKa plus log base, conjugate base, or salt over acid. Why did I use this? Because this is an acidic buffer. How do you know there's an acid? Weak acid with its salt. Do I know concentration of the salt? Yes, given to me right here. Do I know concentration of the acid? Yes, given to me right here. Remember, these are concentrations. Do I know pKa? No, but I know Ka, which means I can solve for pKa. What is pKa? pKa is going to be negative log of Ka. Remember, P in front of anything is negative of log of that thing. So negative log of 1.8 times 10 raised to the minus 5 will give you pKa of 4.74. So this is pKa of my acetic acid. So what is my pH? pH is going to be 4.74 plus log 0.50 molar divided by 0.50 molar. This is cancelled, you get 1, which is 4.74 plus log of 1, which is 0, which essentially gives you 4.74. So that is your answer for this question. Comes very easy when you use Henderson-Hasselbalch. You could also use the whole equation thing where you can use ice table to do this, but honestly it's not needed if you know Henderson-Hasselbalch. Only remember, you can only use this for buffers though. Okay. Let's try another one. Determine the pH of a buffer solution containing 0.25 molar benzoic acid and 0.6 molar sodium benzoate. So this is a buffer. If the question doesn't tell you it's a buffer, you should be able to recognize it's a buffer. How? It would consist of two components first to begin with. One of those is going to be a weak acid or a base, and the second one is going to be the salt of that acid or base. So you can see here what I have is benzoic acid, which is a weak acid, and I have benzoate, which means it's coming from this acid. It's a salt, sodium with benzoate. So this is a salt, and that's it. That makes it a buffer. So even if this term buffer was not used in question, you would know it's a buffer. How do we find pH of a buffer? Simple. pH is pKa plus log salt over acid concentration. pKa here again, I can find Ka is given. pKa would be negative log of 6.3 times 10 raised to the minus 5. Which is 4.20. So what is my pH? pH will be 4.20 plus log concentration of salt. Salt in this case is benzoate. So you have to be able to recognize what is your salt and what is your other component. Acid is 0.250 molar. Remember, they have to be concentrations and they have to be same unit in order to cancel. And if you plug this into your calculator, it will give you the final answer as 4.58 as your pH. So this is my final answer. Moving on, we have a different type of question. In this case, it's not directly saying what is pH of this buffer. There is a buffer, but we have added something into the buffer, and it's asking what is the pH after you added something. So it says calculate pH of 1 liter of a buffer solution containing 0.5 molar of CH3COOH and zero point 0.5 molar of acetate, sodium acetate, after 0.02 moles of solid NaOH was added, which means you have a buffer already made, but to the buffer you have added some sodium hydroxide. Now the question is asking what will be the new pH of this buffer. Okay, so now if you add sodium hydroxide into the buffer, remember buffer consists of two components. One is acid, one is the base. This base that you added from outside is going to react with one of the components. Which one? This is an acid. This is a weak acid in my base, and this right here is the salt, which means this is the conjugate base. What are you adding from outside? NaOH, which is a very strong base. Who is the base going to react with? The base is not going to react with the base. The base is going to react with the acid, which means there will be a chemical reaction here. So I have to write that equation. I have CH3COOH in the solution. You're adding some NaOH from outside. So this is going to react and it will produce CH3COONA. How do I know? The cation of the first is going to react with the anion of the second. Oops. The cation here is H ion, is going to react with the anion of the second. The anion and the cation are going to react. Double displacement reaction. Okay, this is acid. The Na is the cation. It's going to make this salt with it. Acid and base always react to give you salt and water. So this is how they are going to react. Now I have to figure out at the end of the reaction what do I have left. Okay, so this is not an ice table. This is a chemical reaction, and the table that we are going to make is basically a reaction table. Okay, the reaction table essentially includes your initial, it includes the change, and it includes the final concentration. This is not an equilibrium reaction. This is just a one-sided reaction that is occurring. We just have to find what is the final, what do I have at the end after the mixing is done. So let's write down what did I have initially. Now one more thing you need to remember here, in this case you can work with either moles or molarity. Okay, remember in ice table we always use concentration, which means we always use molarity. Whereas if you are making a reaction table like this, which is initial change and final, we usually use moles in this case. We cannot use concentration, okay, because this is based on limiting reactant. However, in this case, you could work with molarity or you could work with moles. It would not make a difference. Why? Because the final volume for all of them is same. Molarity is moles over volume, moles over liter, and moles is what? Molarity times the liters. In this case, molarity is given to you and liter for all of them is same, 1 1 1. So if you want to find moles of this, you would do 0.5 times 1, 0.5 times 1, 0.002. So in this case it doesn't matter if you use moles or molarity, but remember whenever you're doing a table like this, use moles and not molarity. Molarity we only use in ice table. In reaction tables we use moles. Okay, so we'll start with moles. We'll do it the right way. Moles of CH3COOH is molarity times volume, which is 0.50 moles. What is the initial moles of CH3COONA? 0.50 moles again. What is the moles of NaOH you added? 0.020 moles. Water, I don't care because it's not really participating. It's not moles of water. It's a liquid. It's a medium where the reaction is happening. And it also doesn't affect our pH, so we don't care about it. Now this is similar to ice table. Okay, first we have to identify which one's limiting reactant. How do we do that? If you remember the concept, limiting reactant is the one that finishes first. Okay, and it controls how much product is made. So this is 0.4, this is 0.02, both are 1 to 1 mole ratio. Everything is 1 to 1 mole ratio, which means this is my limiting reactant. This will finish first. So how much of this will be used? All of it, because it is my limiting reactant. So change is 0.02. For every 1 mole of NaOH, I use 1 mole of CH3COH. So for every 0.02 moles of this, I will use 0.020 moles of this. So there's no change. This is kind of like ice table when you do minus x plus x. Same thing, but now we are working with moles instead of molarity. This would be plus 0.020 moles. So at the end, finally, what do I have? I have 0.5 minus this much, which would give you 0.48 moles of this. This would be 0 and this would be 0.0520 moles of this. Okay, so this is finally my reactant, and this 0 would not be here because we are doing, if we go by decimal places. Okay, so that is how many moles of each are left at the end. So what do I have at the end of the reaction? I have CH3COH, which is the acid, weak acid, and I have the salt, which means what do I have here? Again, I have a buffer. And how do I find pH of buffer? pH of buffer is pKa plus log salt over acid. What is my salt? This is my salt. This is the acid. Do I know the concentration of salt? I know the moles. Can I find concentration? Yes. You take the moles, divide by volume, which is liter. In this case, it's 1.0 liter. The question tells you. So 0.052 molar. That is my concentration. Remember, in this case, numbers are same and they're not matter that much. And that is only because the volume that you have is essentially 1 liter. But it would make a difference if the volume is not 1 liter. What is the concentration of the acid? 0.48 moles over 1.0 liters, which is 0.48 molar. Now you have the molarity. Plug those in. Other number that I need is pKa. How do I find it? Ka is given to me. So this is going to be negative log of 1.8 times 10 raised to the minus 5, that's pKa, plus log of salt, which is 0.052 molar, divided by 0.48 molar. Oh, oh, no, 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 wait, I made a mistake here. That's not 0.052, 0.52. Yeah, my bad. We are adding this will give you 0.52 moles. Okay, that was my mistake, my bad. So it would be 0.52 divided by 0.48 molar. Plug all of this into your calculator and that would give you your final answer as 4.77. That is the pH of the solution after the reaction is done. How can you also confirm this? Theoretically, you had a buffer, okay, and you added NaOH into this, meaning you added base into this, so your pH should increase. Initially, if you do not add this base, your pH would be negative log of pKa, 4.74. Now it has increased slightly to 4.77. It's okay if you don't understand this, what do I mean by increase, as long as you understand how to do this question. This is how the questions would be like, okay? You need to know a reaction. If a reaction is occurring, find what do you get at the end. Same process. What do you get at the end of the reaction? Is it a buffer? Is it a salt? Is it a strong acid or strong base left? And you decide how will you calculate the pH based on that term. I have one more question on the similar concept. Question is, calculate pH of a 1 liter of buffer solution consisting of 0.5 molar acid and 0.5 molar sodium acetate after adding 0.02 moles of HCl. So now you had a buffer. The question is asking calculate the pH after you added something like this. Again, which means this is where a reaction is going to occur. Okay. If you're mixing things together, there's a chemical reaction. So you need to first know what components do you have. This is what? CH3COH. This is the weak acid. CH3CONA. This is the salt or weak base. Okay, how do you know? Remember the salts? They have iron comes from strong, comes from weak, similarly in that manner. Or if you know this is a buffer, the question says it's a buffer, which means this is the base, conjugate base. What are we adding? HCl, which is a strong acid. So if you add acid, which one is it going to react with? It is not going to react with the acid. The acid you add is going to react with the base, which means I will have a reaction of these two. CH3COONA is going to react with HCl and will give me products. How do I know what are my products? Remember, cation of the first, Na plus, will react with anion of the second. So Na and Cl will react to give me NaCl. Whatever's left will react with each other and will give me CH3COOH. So this is the reaction that is occurring. Now, what if it's a chemical reaction and I need to find what is the concentration at the end? I will use the ICF table or the reaction table. It's not an ICE table. This is not equilibrium. This is a reaction table. What do I have initially? I have 0.5 of acid, which was this 0.50 molar of this. I have 0.50 molar of this. Again, these are molarities. Remember, in this table, I cannot use molarity. I have to use moles. So first convert these molarities to moles. Molarity is moles over liter. So moles is molarity times liter. What is molarity? 0.5 liter 1, which means it is same number but the unit changes. It's not molar, it's the same number but in moles. Again, this is only true here in this question because it's 1 liter. If it's different, then you will use the actual moles. After adding 0.020 moles of HCl, so we added this much HCl. Okay. Do I have NaCl in the beginning? No, so it's 0. Now let's do what would be the change. Which one's limiting? Again, HCl is limiting here, so negative 0.020 moles. Negative 0.020 moles, 1 to 1 mole ratio. This will be positive 0.020, positive 0.020. What will I have at the end? I would have 0.48 of this, 0 of this, 0.02 of this, and 0.52 of this. These are again all moles. This is my final. Okay, these are my final values that I have. What do I have at the end? I have some of the salt left over. I have some of the acid left over, weak acid left over, and I have some of this salt also left over. Does this salt affect the pH? NaCl comes from strong acid. Cl comes from strong acid, this comes from strong base, which means doesn't affect the pH, doesn't affect the pH. So this I don't care about because it does not affect the pH. I'm interested in pH. pH only depends on this and this. Salt with its acid means it's a buffer again. So how do I find pH? pH is pKa plus log salt over acid. In this case, it is going to be negative log of 1.8 times 10 raised to the power minus 5 plus log of salt, which is 0.48 divided by acid, which is 0.52. When you plug this into your calculator, this will give you a pH of 4.70. So that's your finalize. Okay, so this is how the questions of buffers are going to be worded. Either it's just simple find the pH of a buffer, or you add something to the buffer, and then at the end of the reaction when it's done you have to find what is pH of that buffer solution. The next type of question you can get in a buffer is preparing a buffer. How would you prepare a buffer? For instance, you know you want to make a buffer out of, let's say I want to make a buffer of acetic acid and sodium acetate. I want to make this buffer, but how do I know how much of this to add and how much of this to add? So that question can be answered using this approach of preparing a buffer. There is an approach to doing these questions. Okay, so we'll look into that. But first thing is, if you want to prepare a buffer, you need to know the pKa of the acid. Okay, and how do you know which buffer, if this buffer will work for you or not? The only way to know if this buffer will work for you or not is the pH range, buffer range. Remember that was pKa plus minus 1. So if you want to make a buffer that works around pH 3.5, only then you can make this buffer. Okay, so first thing is identify if this buffer will work for you or not. Second thing is we'll use the Henderson-Hasselbalch equation to find a ratio and then calculate how much of each do we need. Okay, so let's try a question to understand that. For example, this is a question: an environmental chemist needs a carbonate buffer of pH 10 to study the effect of acid rain on limestone rich soils. How many grams of sodium carbonate must she add to 1 liter of freshly prepared 0.2 molar sodium bicarbonate to make this buffer? So first thing we understand from here is that you need to make a carbonate buffer. The pH of the buffer should be 10 once made, and the question is asking how many grams of the salt. Sodium carbonate is your salt. So how many grams of the salt should you add to 1.5 liters of sodium bicarbonate? Molarity is given. So these are the two components that we have in the buffer. One is Na2CO3, another is NaHCO3. The question is you have to mix these two and make a buffer. Somebody might say, okay, both are salts. How are we making a buffer out of this? Both are not salts. See here, both are salts, that is correct. But both are not just salts. Okay. Ka, you can see, is given of HCO3 minus, which means this HCO3 minus is acting as your acid here. Where is HCO3 minus? Right here. So this is your acid and this is the salt. Okay, how do I know this? Remember, both are salts, but also remember salts can act as acids and bases. Now you know it from the previous video. Sodium here comes from NaOH, which is a very strong base, which means this is not going to affect the pH. HCO3 comes from H2CO3, which is a weak acid, which means this is going to affect the pH. Okay, so this, and then the second one here is Na2CO3, which is again coming from Na, so it will not affect the pH. This is CO3, which is again coming from H2CO3, which means this can affect the pH. How are these two mixed together going to affect the pH? The essential reaction is going to be, you have HCO3 minus, this is going to dissociate to give you CO3 2 minus and H plus. Okay, so if you mix it with water, essentially this hydrogen will be donated to this water, and if you want to include water, you can simply say that this is going to make H3O plus. So this is your acid and this is the salt, and they together make a buffer. Okay, but again, that was me explaining you how this is a buffer, but the question is not asking that, so we don't care about any of this info for now. The question is asking how much of the salt component do you add? How many grams of it do you add? How would you do this? There's only one way to do these questions. Okay. First thing, we use Henderson-Hasselbalch equation, which is, if let me write the equation back again so it's clear which one's the acid, which one's the base. This is, remember, my acid, and this is the base, or you can call it the salt, Na2CO3. Okay. Now, how would you know? The question tells you that this is 0.20 molar and you have 1.5 liters of this. Question is asking how much of this to add in grams. Remember, this is not a question about stoichiometry, what you learned in general chemistry 1. It's not saying if you have this much of this, how much of this will be produced. That's not what the question is asking. The question is asking, you have this, how much of this to add to make a buffer so that your equilibrium can be set up. Okay, so don't do stoichiometry here. This is a buffer, so we'll use Henderson-Hasselbalch equation. What do we know from there? pH is pKa plus log salt. Salt for me is CO3 2 minus over acid HCO3 minus. Okay. Now here concentrations. Do I know pKa? Do I know pH? First thing 10. Perfect. I know pH is 10, what I want. pKa. Ka is given to me, so I can find pKa. What is pKa? pKa will be negative log of 4.7 times 10 raised to the power minus 11, which will give you pKa of 10.33. So 10.33 plus log of carbonate ion, which I don't know, I need to find it, over bicarbonate, that is given to you. The concentration that we need for it is 0.20. So you plug this in, and from here you can solve for carbonate ion. How would we solve? This is 10.33, 10. So if I minus 10.33 from here, I minus 10.33 from here, that would give me negative 0.33 here equals log carbonate over 0.20. Now I need to get rid of the log. How do you get rid of log? You take anti-log. This is log to the base of 10, which means if I raise everything to the power of 10, it would get rid of the log for me. So if I do 10 raised to power of negative 0.33, I'm putting negative because there was a negative sign right here to begin with. Okay, equals, when you take 10 raised to power of this, that would get rid of log, and what you're left with is carbonate over 0.20. So what is my carbonate? CO3 2 minus is going to be this 10 to the power of whatever this is, 0.33 multiplied by 0.20. If you plug this into calculator, it gives you 0.467 times 0.20, which gives you how much is the concentration? 0.094 molar, which means this is how much molar my carbonate should be. This is molarity of carbonate. Now what does the question want? Question wants grams. So now you need to use your prior knowledge from general chemistry 1, which is, if you know the molarity of a solution and you know the volume of your final solution, how do you find how many grams you need? You first use molarity and volume to find the moles, then you can convert moles into grams using molar mass. So this comes from general chemistry 1. Volume, I know I need 1.5 liters. So I can find moles. Moles will be molarity times volume, 0.094 multiplied by 1.5 liters. In liters, remember, that would give you the moles, which is 0.140 or 0.14 moles. Once you have the moles, you find the mass or grams using moles. I need more space, but I'll do that here. 0.140 moles. Use molar mass. 1 mole is molar mass of the sodium carbonate. How would you find molar mass of sodium carbonate? Use your periodic table. Na2CO3, 2 sodium, so 2 times 23.00 plus 1 carbon 12.01 plus 3 oxygen 16.00. Total molar mass comes out to 105 or 106.01 grams. Plug that in here, 106.01 grams. Mole cancel, your final answer is in grams. This is how many grams of sodium carbonate you would need, and the final answer that I have is 14.84 grams. If you're using some different numbers of molar mass, slightly different numbers, that's totally fine, as long as, because you might be using a different periodic table, but ideally it should be close to 14.8 or something. That is how you can prepare a buffer. If grams are given, molarity is given, so basically your idea is, your most important thing here is Henderson-Hasselbalch equation. It's not about the moles or molarity, that is from general chemistry 1. What's important here is you need to use Henderson-Hasselbalch equation, find this, find out these, solve for these moles or molarity. If the question is asking molarity, use molarity. If the question is asking volume, find the volume. If it's asking grams, you use this approach. So as long as you have this equation, your answer lies in this particular equation. Okay, apart from acid, there's one more buffer. There's one more topic that I just want to briefly mention, which is polyprotic acids. It's not very too much detail in this topic. We just want to touch, and so that we know, if you see this name ever, you know what exactly a polyprotic acid is. So what is a polyprotic acid? It's an acid that has more than one ionizable protons. What does that mean? For example, HCl, HBr, HI, HNO3, when they act as acid, they have one proton, only one hydrogen that they can donate. Proton means hydrogen ion. So these are called as monoprotic acid. Protic here is coming from protons. When they can donate only one proton, they are monoprotic acid. If an acid has more than one hydrogen that it can donate, those are called as polyprotic. Example, H2CO3 can donate 2 hydrogens. H2SO4 can donate 2 hydrogens. H3PO4 can donate 3 hydrogens. So these are polyprotic acids. Sometimes there's also a term used as diprotic, which basically means you have 2 protons. Like these two are diprotic acids. Okay, anything more than that, that is definitely a polyprotic acid. Now polyprotic acids, for example, if you take example of H3PO4, you put it in water, it will act as an acid, it will donate one of its proton at a time to water. One is gone, which means it will make H2PO4 minus and what? Proton in water. Now this is also an acid, which means it can also donate its one more proton into water. So when you mix this in water, it reacts with water, gives one more proton away, and it has HPO42 minus and H3O plus. This right here can also act as an acid. When it mixes with water, it has one more proton that it can donate, that would lead you to PO4 3 minus. So each of these, this is an acid, this is also an acid, this is also an acid. So these three are different acids, and therefore because there are three different acids, they have three different Ka values. Even though it's the same phosphoric acid, but when it loses one proton, it's a new acid. When you take away one proton from here, this is a new acid, this is a new acid. So these are three different acids, that is why they have three different Ka values. Okay, this is Ka1, Ka2, Ka3. So three different acids, three different Ka values for the same polyprotic acid. And what you need to remember here is that these Ka values are always going to be arranged in this manner, which means the Ka for the first proton that is lost is going to be more stronger than the Ka of the second, and then the Ka of the third. Okay, so this is basically telling you strength of these acids. always, if you have a polyprotic acid, the first acid out of all of those is stronger out of the rest, then the second, and then the third. The third hydrogen, or the last hydrogen, whenever it is lost, it is the weakest of all three. H3PO4 is a weak acid to begin with, right? Which doesn't mean that this is a strong acid. This is still a weak acid, but when you compare these three weak acids, this is weak, this is weaker, and this is the weakest. Or this is the strongest out of the all three weak acids, if that makes sense. Okay, so that's the only thing with polyprotic acids. Usually the proton, when the first proton is lost from polyprotic acid, that is a stronger acid of all the rest of the protons lost from the same acid. Like you can see in this table, there are some of the acids. Oxalic acid has 2 protons, so it has 2 Ka values. Sulfurous acid has 2 protons, it has 2 Ka values. Phosphoric has 3, so it has 3 values. Arsenic has 3, so it has 3 values. Okay, so that basically tells you that different acids, if they are polyprotic, they will have different Ka values. The first one is always going to be a bigger value compared to the second one, and then the least would be the third one, like you can see here. -3, -8, -13. So that's the order. First one is always the strongest of them all, then the stronger, then the weakest.